Okay, so we're going to keep talking about this differential equation first order, and I'm going to introduce you 2 or 3 more kinds of a first order differential equation, right? Yeah. Okay, so what we talked about in the last lecture is this kind of. Now, what we call this one here, we call this is a non-homogeneous and it is also linear ODE, okay, because it's linear, right? So, so now let's take a look at another type. What we called it's called separable equation. Okay, separable equation. The general format of the separable equation is this. So you have a y prime equal to f xy, like this. And this function f of xy can be separated into 2 functions. One function is purely a function of x, and the other is a function of y. So this is so-called a separable equation. Okay, yeah. Okay, so now in order to be consistent, let's change this t to x set it here. Okay, let's change this t to x. Now, what is the connection between this kind of and this kind of here, right? There's a connection, but first of all, okay, you need to understand when you have such kind of a differential equation, it's linear, okay? But when you have such kind of this equation, this so-called separable one, it doesn't necessarily is going to be a linear, right? See, for example, right? Here, example, I have y prime equal x e to the power of x plus 2y, okay? Right. So this whole right side is a function f of xy. Okay. Now, if I do a little manipulation at here, I can separate this e to the power x plus 2y into 2 portions, okay, like this, right? Yeah. And as you can see now, these 2 terms, that's basically a function of x. And this term here, that's basically a function of y. Okay, right? Yeah. So that's this one here satisfies this format here. Okay, this format. So you can separate this f of xy here into 2 portions like this. However, okay, if I ask you, is this differential equation a linear or non-linear? Right? What would that be? It's a non-linear, right? So it doesn't satisfy the standard. Sorry, this is a 1 prime here, isn't it? Right? It's a 1 prime. It doesn't satisfy the standard format added here. Okay, it doesn't satisfy because there is a exponential term to the power of y. Okay, yeah. So this is separable. Okay, this is separable. However, if you have this kind of a function here, okay, this one, so y prime equal to 3x minus y, right? So you look at this one here, what is it? This is basically this standard format, huh? Right, it's equivalent to saying this is y prime plus y equal to 3x, right? 3x, okay. However, okay, here's your f of xy here, but this guy, okay, in this case here, you can't separate it anymore, right? You can't separate into a function of x multiplied by a function of y. Okay, so this is separable, and this is not separable. Okay, so that's a difference here. Now, how do we solve this kind of separable equation? It's actually very simple. Okay, actually very simple. All you need to do is this. So go back to the first, the general format here. So what we have is basically the dy over dx equal to x function x, y function y, right? Yeah. So just like the first technique we learned, separating variable technique, right? Separating variable techniques is used on what kind of format? Separating variable techniques is used on homogeneous, right? Homogeneous. So as a matter of fact, if you let this term equal to 0, right? If you let this term equal to 0, the y prime equal to px yx, it's actually what? It's actually turned out into this separable equation, right? It's actually turned into a separable equation. So here we separate the variable. So dy over capital Y here, capital X, small x, and dx. So separating the variables. So this is what you call separating variables. Then you integrate, right? Then you integrate. So that's it. That's basically the approach here. Okay? Yeah. So the key point, the first key point is, I guess, you need to be able to distinguish or tell, oh, this is a separable function here. So I can separate it into two portions and then apply this technique here, right? Yeah. Okay, so that's the this technique here. So let's take an example. Yeah. Let's take an example here. This one here is so y prime equal to 4x plus 1 plus 2ey. Okay, this one. Maybe I should write down one. This is a nonlinear. Okay, so let's take a look at this one here and see if we can use if this satisfies this separable equation or not. Okay. So here the whole right side is f of xy here, right? F of xy. Yeah. Okay. So I think I can call this 4x as this capital X of x, and I can call this term as capital Y of y, right? So there are two functions basically. Okay. Yeah. So then I'll just write this side here as dy over dx, and then I'm going to move all the y together, move all the x together. Okay. So I'm going to have dy. Move this term together, so that's 1 plus 2ey over here. And 4x and dx like this. Okay. So then you integrate. Okay. Then you integrate. So this is a very simple integration. So this side here is 1 plus 2ey. You can integrate separate. This is 1, so that's y. Exponential terms the same as it is, okay, and the other side 4x, so 2x squared and plus a constant c on one side, and that's it. Okay. So let's say, suppose I have an initial condition. Let's see, I have a initial condition y of 0 equal to 1. Okay. So now I can solve for the constant c, and y of 0 equal to 1. So this basically means y of 0 plus 2e y of 0 equal to 2, 0 plus c. Right? So that's applying initial condition. And y of 0 equal to 1, so 1 plus 2e1 equal to c. So c equal to basically 1 plus 2e. Right? Okay, so this is the way to solve this kind of separating variable, separable equation. Okay, separable equation. So you need to understand is, be careful is, separable equation doesn't necessarily is still the linear equation. Okay, like this one here. Okay, chances are it could be a nonlinear equation. Right? Yeah. So many times solving nonlinear equation is not that easy, but for some nonlinear equation, and as some of the nonlinear equation, I'll show you some stuff of other type, you can apply these techniques. Any questions? All good? Okay. One of the assignments, I think it's like this is separating variable technique. Okay. Yeah. One of the assignments for assignment 3b is dr over d theta equal to b dr over d theta cosine theta plus r sine theta. Okay, so this one here. So how many of you have done it? Oh, many of you. Good, excellent. Yeah. So did you can apply this separating variable you can apply separating variable. Yeah, I wonder what did you apply? Did you use integrating variable technique or did you use a separating variable technique? Separating variable technique, yes. Yeah. You actually, if you use integrating factor methods, it still works. Yeah. Okay. So bottom line is, okay, combine all the common terms together. Okay. Because I have a dr over d theta here, I have a dr over d theta here, right? So you combine all the similar terms together. Okay. There. So that's the after the simplification, that's what you have here. Now, when you look at this one here, okay, let's say what kind of a differential equation it is, right? So if I move this 1 minus b cosine theta to the right side, I get b. I get this, right? I get b sine theta over 1 minus b cosine theta r. Okay, so I get this one here. Okay. So see when you look at this one here, right? So you can see now this is you can call it if you move this whole term to this right side, that's basically homogeneous. Right. First of all, you can see that's a homogeneous, right? That's a homogeneous linear ODE. Can you see that? If I move this whole term to the right side, so okay, so this is the first appearance it looks like. Okay, that's what it looks like, right? This is exactly what kind of type is it? It's basically y prime plus p t y equal to 0. That kind of format, right? That kind of format. What do we call this? We call this homogeneous, and it's linear, right? It's linear. Okay. And if I don't do this transformation, if I don't shift this to the left, if I just look at this one here, and for this guy here, I have two terms here, right? I got two terms. So this is f r theta, right? This is a function r theta. It's like a function x and y, right? Yeah.
Why did you dr become
dr? Not negative. Sorry, just just saying this is the first. This is the first look. If I do this, yeah. So the second the second way looking at it is you don't change that. You still keep it as it is. Now, as I said, this is a function of r theta, and here is a function of let's call it r, and the first term is a function of capital theta, right? Yeah. So that's the separable equation. So for this particular one, you can put it in the category of a linear homogeneous differential equation, first order. You can also put it in the category as a separable equation. Is that clear? Yeah. Okay. So, yeah.
Let's say instead of r, it was sine of r. Would it still be linear?
Instead of come again. Instead of r, and it becomes sine r here. Yeah. It's not going to be linear. If this is sine r, you mean like this?
Sine of r, yes.
Yeah, no, it's not going to be linear. It's going to be non-linear, but it's still going to be a separable equation. Is that clear? Yeah, that's a good question. Yeah.
It's still going to be a function of r, right?
Yeah, it's still going to be a function of r, but it's not going to be a linear one. See, linear, you cannot have a sine r here. Right? This is a linear format. Okay. Yeah. Good. So how to solve that? Just use a separate variable. You can solve it. Okay. So that's the first. That's this separable equation in here. Separable equation. So let's take a look at this. The other one, I'll call it homogeneous equation. Yeah, this is the terminology here is a little confusing now. Nothing homogeneous equation. Didn't you just say that this is homogeneous, isn't it, right? This is homogeneous here. Yes, we call this a homogeneous ODE, okay, ordinary differential equation. But here I don't have ODE here, I just have homogeneous equation here. So we'll explain what this one looks like. Okay. Come back to the general format. Okay, general format of a first order differential equation. Okay. So this is a general format, right? Okay. Now, for a certain situation, this function f at here, there is a property for this function f. Okay. So what happens is, let's write down this in certain cases. Okay. What happens is, when you replace the x with lambda x, and when you replace the y with lambda y, okay, and you will find out that it doesn't change. It still goes back to itself. So for certain function f of x, y, so basically in certain cases, when you replace the x and y with lambda x and lambda y, lambda is a constant. Okay, a certain constant. It doesn't change. It goes back to itself. Okay. So when you have such kind of case, what we call it is, we call fxy, okay, is homogeneous. It's a homogeneous function of degree 0, okay, of degree 0. So that's where the name homogeneous from. Okay. So for example, right? For example, I might have a function fxy equal to this. Okay, equal to this. So here's a function fxy, right? So let's see. Is this function a homogeneous function of degree 0? Basically, if I replace x and y with lambda x and lambda y, do I get back to my original fxy? Right? Okay. So what do? We replace x and y with lambda x, lambda y. So what do I get here? Lambda x, lambda y at the top here, right? Bottom, lambda x squared, lambda y squared. So you can easily see that at the numerator there's lambda square, at the denominator there's a common lambda square. So you get those lambda square canceled. You get back to self, right? Get back to self. Okay? Yeah. So this function is a homogeneous function of degree 0. Okay. Is that okay? Yeah. That's the definition here, okay? Now, there are many similar examples. I'll give you, you can verify yourself, okay? For example, this one here, ln negative 3x squared y over x cubed plus 4xy squared. Now, sometimes the first looking at this one here doesn't appear to be a homogeneous. It's hard to tell actually, right? But I'll show you a technique here. You know, you'll be able to tell that quickly. You don't have to do this every time like this, right? Yeah. So the bottom line is, okay, yeah. Well, we'll see. Well, yeah, not here. Yeah, not here. Later. Yeah. Is that good? So in general, you might wonder is, okay, so this is a homogeneous function degree 0, then there must be a function, something like a homogeneous function of degree 1 or 2 or 3, right? Yeah, that's true. So, for example, in general, in general, if I do this, okay, if I do this, and we got lambda to the power of n of this, we got this. So this is called homogeneous, okay, homogeneous function of degree n, okay, degree n. So you can see now when you replace the n with 0, right? That's what we got for our simplest case over here. Okay, simplest case over here. So we're going to focus is on the degree of 0 here. Okay, that's what we do. Okay. So let's take a look at the problem of how to solve. Okay, how to solve such kind of a homogeneous equation, which means the function f of xy can be, and the function x1 can be called a homogeneous function of degree 0, right? Yeah. Okay, so what we do is this. We have a function of this, right? We have function of this. So let's use this example here. Right? Let's use example. So let's try this. When you look at this one here, let's divide both this numerator and denominator by x squared. Okay, do this. And if we do this, the top one becomes, right, what does the top one becomes? Y over x. Yeah, you need this x. I think lots of people making mistakes when such thing happens. The bottom line becomes x squared over x squared is 1, y squared over x squared is y squared over x squared, but I can write it as this, right? Okay. So that's what happens. Now you see, originally this is a function xy here. This is still function xy. However, when you have such kind of expression here, this expression at the same time, instead of x, it's a function of xy. At the same time, it's also a function what? Y over x. Okay. So this is a function of. So you can call this is a function. I'll use a different symbol here, capital F here. So this is a function of y over x and here, okay, y over x. So in other words, so this is basically the shortcut I was trying to show you. How do I know whether this is a homogeneous function of degree 0? You do this. As long as you can transform your original fxy into a function of y over x, then it is guaranteed a homogeneous function of degree 0. Is that good? Yeah. So actually quite simple, because if I have this form here, y over x is a ratio, right? If I replace the y with lambda y, x with lambda x, the lambda doesn't really work. You know, lambda just got cancelled. Okay? Yeah. Okay, so now I'm kind of clear now, and clear basically means as long as I can transform this one into here, I'm guaranteed to have a homogeneous function of degree 0. So the question here is, how do I solve this one here? How do I deal with this y over x at here? Okay? So what we do is we use a so-called transformation technique. It's a transformation of variable technique. So here's what happens. You let u equal to y over x. Okay, you let u equal to y over x. So again, I don't need you to remember any formulas here. Okay, and I need you to remember these procedures. Okay, so you let u equal to this. When you let u equal to this, excuse me, your original function y over x will simply becomes f of u, right? Or simply becomes this. Now at the same time, because u equal to this, that means y equal to ux. Right? Yeah. Okay, so y equal to ux, I'm gonna take a derivative of both sides of this equation. Okay, take a derivative. So taking derivative. If I take a derivative, and this side just becomes y, right? Y prime. And the other side is a ux, so there are two functions. So then you need to use product rule. All right, product rule. And product rule means I will take derivative u first, then x, and then take derivative x. So derivative x itself, it's 1, so you end up with u. Right? So the u at here is function of x, okay? Function of x. Because y is function of x, so ultimately the u is a function of x. Is this step clear? Okay, good. So this step here, this little results directly from our substitution here, okay? Yeah. Yeah, derivative x over x is 1, yeah. So this results directly from this transformation, from this type of substitution. Well, don't forget that we have, right, what we already have here is, right, we were given y prime equal to fxy, right? This is what the question will be given to you, right? You're required to solve this one, okay? You're required to solve this. And fxy, where's fxy? Fxy, you're solving this when fxy can be written into this format. So fxy is this, right? Is this. And we're defining u equal to this, so that's basically this. Okay? So basically, this is given. This is given here. And this is what you derived based on your transformation, okay, from yx to u. In other words, see, they're both y prime, right? They're both y prime. So you want to solve, then that means this term has to be the same as this term here. Does that make sense? The logic here? No? So this one is what you imposed here, right? This is what you imposed. You let u equal to this. And then naturally, y equal to ux. And then y prime equal to this. Okay, that's based on what you imposed, the condition you imposed here. And this one here, it's not imposed, this is given. This is what you're going to solve, right? This is what you're going to solve. So then, in order to solve this, both having a y prime, So that means you have to make this to be the same as this. Okay, so you have to make u prime x plus u equal to this. Okay, you got to make this equal to this. Otherwise, you can't solve, right? What's the reason that you impose this condition? Because we're trying to solve this. Okay? Yeah, you might wonder, how do you know you're going to impose that you're going to be able to solve? Yes, I know, because you'll see why it happens, right? So this is basically the logic here. You impose this, and you have the original, and so then you have to let the results from what you imposed to be the same as the original. Then we can solve. So I make this equal to this. When I look at this one here, right? When I look at this one here, and I'll do one more step right here. So this u prime is du over dx. X. I'll move the u to the other side. Okay. To the other side. And then I'll move the x to the other side too. So looking at this portion right here, looking at this, what kind of equation do I have here now? Separable equation, exactly, the first type here. This is a separable equation. Okay? So separating variable. So you do du over f of u minus u, and 1 over x dx. Then integrate, okay, based on the conditions. So once you integrate, you'll be able to get the u equal to something, right? You will get u equal to something. And what is the u? U is y over x, right? So then you can get y equal to something. So that's the idea. So you'll be able to solve this, okay, based on these procedures. Okay, so understand these procedures here, okay? So let's take an example. Here's the first order differential equation. We'll impose certain conditions. Okay. Solve this guy. So we're solving this under this scenario. I guess you probably should know. Well, this fxy must be a homogeneous function of degree 0, right? Yeah. But the question is, how? How do you write that into the format? Basically, can we write this one into this format here, right? Can we make it into this format? Okay. That's essential here, right? Once you're able to do this, then you know that you're dealing with a homogeneous function, equation right here. So can you manipulate this one here? Okay, can you manipulate this one? Somehow write it into this format here. So that's a little skill I need you to have. Okay, yeah. Midterm you don't have to, but final maybe. Yeah. So what would you do? Separate them out. So basically, you want to do this, right? So that's perfect. This is already y over x, right? That's already y over x. But what about this guy here? Does that really still satisfy this format here. That's right. So yeah. So basically, you can move this x squared into the square root, right? So it's like this. So this is x squared minus x squared y squared. Bottom here, just make it as root x squared, right? Root x squared. So then the whole thing becomes a root here. So x squared minus y squared over x squared. And that's y minus y over x. Okay, that's this one, right? That's the simplest you can get, and this is f y over x. Yeah. So take a look at this, how this is being done, right? If you're proficient, sometimes you can skip all the steps, just directly go from here to here. Okay. Yeah. It's necessary. It's very necessary. Otherwise, you won't be able to solve it. Even if you use that f lambda x lambda y, you check this equal to this. You said yes. Okay. But if you can't write this one into this format here, you'll give you a hell of troubles in order to solve this one here. Okay? Yeah. So this, you have to be able to write this one into this format. So then the next step is to let u equal to y over x. Okay. So we're basically going through this whole procedures again. And y equal to ux, right? Y equal to ux. And here is your function fxy here, right? Or capital function y over x here. So since I'm letting u equal to y over x, so this function is basically fu equal root y minus u squared plus u, right? Plus u. So my original differential equation, right? My original differential equation becomes, what's my original differential equation? The original differential is this equal to this. So that differential equation essentially becomes y prime equal to f of u, right? So without any changes, y of u. So this whole side is function u here. Based on your condition, the condition you imposed at here, we have y prime equal to u prime x plus u here, okay, plus u. So this has to be same as this, okay, has to be same as this. In other words, this du over dx x plus u got to be the same as what? Got to be the same as this. Any questions? Yeah, is this following here? Okay. These two cancel, right? These two cancel. And we're left with du over dx x 1 u squared. Or separating variables. So du over this equal x dx. 1 over x dx, right? Yeah, 1 over x dx. Is this clear? Yeah? Okay, so now you integrate. Integrate. I guess this is very simple. This is just ln x here, right? Ln x. What's this integral? Cosine, that's right. Sine or arcsine, right? Arcsine, yeah. And I need to plus a constant either left side or the right side, doesn't matter. So I don't have the absolute sign here because my original question says x greater than 0, huh? Yeah. So that's it. That's basically pretty much the solution here, but we don't need the solution for the u, we need the solution for the y, right? And so what we need to do is we need to find the solution for the y, because this is arc sine, so that means this is u equal to sine ln x plus c. Okay. Yeah. And what is u? U is y over x. So y equal to x sine ln x plus c. Okay, so that's the solution here. They're very strange solutions, but that's how it is. Is that clear? Yeah. Yeah, you can move the c here, but ultimately it's just a c here, right? Yeah. So your requirements, I mean, in the future is, as the type of a differential equation we learned, there's more and more. So now how many types we learned? 1, 2, 3 types, right? Basically. And there will be 1 or 2 more. So when you see a first order differential equation, then your task is actually to distinguish what kind of a first order differential equation we're dealing with. Is it a linear? Is it nonlinear? Right? If it's a nonlinear, then you can't use the integrating factor methods, and you're going to have to examine that. Is that a separable equation, or is that a homogeneous type of equation? Okay. And then we have another type called Bernoulli type of equation. Okay. Yeah. So those are basically once you'll be able to distinguish what type it is, and you'll be able to solve accordingly. Okay. Get a couple minutes here. So let me give you just one example here, okay? But this is sort of optional here, okay? 1, 2, number 3. We call that exact differential equation. Exact differential equation. So this is a type of differential equation very much associated with 248 that we're learning at here. Okay. Now, before we talk about exact differential equation, and let's talk about what is an exact differential. So let's just suppose I have, let's say I have an expression which is this. So here's an expression, right? Here's an expression here. So you might wonder, what is this right here? Well, I guess it's just a function xy multiplied by dx and a function qxy multiplied by dy, right? Yeah. Have we seen this one here? We have, right? If you recall that, where have we seen this one here? When we were dealing with a concept so-called total differential. All right, total differential. So, when this one equal to df, like that kind of situation. That makes sense, right? Yeah. But so at this stage yet, I don't call it equal to df. Okay? I just say this is an expression. Okay. However, this guy here is called exact differential. Okay, exact differential. If there exists a function fxy, okay, such that fx equal to pxy and fy equal to qxy. Okay, see the logic here, right? So here is an expression. It's going to be called exact differential if there exists a function fxy such that partial f over x is this, partial f over y is a q. So as a matter of fact, what are we talking about? This basically means df equal to this guy here, right? It basically means df equal to this. Okay, this basically means this. Or basically this means this is a total differential. Okay, so it's a total differential of this function f. So that's exact differential. So it's like a kind of different name here. Okay. So I'm going to skip examples. Now, okay, in certain cases, we'll make it into a differential equation. So then, if I have if I have this guy equal to 0, right? If I got this guy equal to 0, and what's this one here? Right? So the expression equal to 0, that's an equation, first of all, right? So it doesn't look like anything. Well, but if you divide dx, okay, if you do this, and what is this one here? What would we call this? That's not necessarily ordinary, but it's a differential equation, right? Well, order is a first order. Okay, whether it's ordinary or not ordinary depends on the function set here. Okay, but this is a first order, right? This is a first order DE. This is a first order DE. Okay. So if I'm asking you to solve this one here, that looks like a pretty complicated because you got x and y tangled here. However, if this function, if this expression, it's basically the total differential of a certain function f, then which means my whole left side here can be written as what? Just a df equal to 0. Does that make sense? No? Yeah. So basically, this whole chunk right here is related to a function f. And basically, it's the total differential of the function f. So that's why I can write this one into this. Now, the question is, if I'm asking on this one, you're basically solving this one. Now, what is the solution of this one? Anybody? What's the solution of this one? No, it's not 0, 0. What's the solution? What do? You integrate. And what's the integration result of this out here? 0. What's the integration result here? F. Well, I guess you plus a c, right? Plus a c here. And equal to a 0. Okay? Equal to 0. Well, in other words, you can call it fxy equal to a constant c when you move this, get rid of the negative. Is that good? So the whole question is, how do I find that f here, right? If I have this one, how do I find it? How do I know this one here is? So that's the trick thing here. We'll deal with that in the next lecture.